So we would come back to the natural looks. And last time we have discussed about the first law of thermodynamics, and in particular, we have already started on the topic of various types of systems. So let me see. Yeah, we have been talking about the first law. Let's see. In the first law, we have various quantities. For example, we have the work done, which is the energy transferred into or out of the system when it is working against a environment. And here we would be focusing on the use of gases system, because in the case of liquids and solids, some of the calculations are very difficult. And as we will see later today, in a gas, the internal energy is actually a very simple quantity that relates only, at least in the case of ideal gas, the internal energy of the gas is related only to the absolute temperature. So that would be a very convenient way to handle the internal energy. And in fact, that would lead to a number of important consequences. So here we have seen the work done, and the work done can also be discussed on the PV diagram of a gas system. So the PV diagram maps out the change of the states of the gas from an initial condition to a final condition. So at here, you have the gas in some initial state, and through some process, it would come to a final state. And in between, there would be a trajectory, there would be a path for the states to change from the initial condition to the final condition. So this is the trajectory from here to here. The area under this path, correspond, well, is proportional to the work done. And in fact, it is the negative of the area that is the value of the work done on the system. So if you are starting from a large volume to a small volume, actually the surrounding environment has to do work into the system, and therefore work done would be positive. Although when you are doing the integration from a large value to a small value, actually you would get a negative area. That is the mathematics. So the work done is related to the area under the curve. And as we show that, the work done depends on the path taken. It varies a lot if you are doing the work along different paths, even though they have the same initial and the final states. So that is something very important to remember. And because the first law of thermodynamics, we would also see that the Q, the heat transfer process, is also process dependent. Depending on different processes, even if you have the same initial and final state, the Q heat transfer is process dependent. On the other hand, P, V, T, and the internal energy, they are state variables, meaning that they could be fully determined by the states where they are. It does not depend on the path. Q and W, they are the transfer variables, which depends highly on how you move from the initial point to the final point. Last time we talked about the cyclic process, which is at here. Let me see. The cyclic process. Which is an important case where the initial and the final state of the whole process is the same. But depending on the path taken, the Q and W would be highly dependent on how this cyclic process has occurred. And here is the first law of the thermodynamics. The first law of thermodynamics states that, at least in the case of a gas system, the internal energy change is equivalent to any external energy input, either be the heat energy, Q, or the work done, W. So in verbal descriptions, it is easy to understand, but of course, you have to calculate in many cases what is Q, W, and delta E. And in order to make up the cyclic processes, there are many different combinations of intermediate paths. So there would be some journeys. For example, in the middle graph, you will see A, B, C, and D. This would be one possibility. And another possibility to have a cyclic process is maybe on the right-hand side, A, B, C, and D, which is a rectangular shaped process. They both start at A and finish back at A. So no change of internal energy. But due to the cycle, there would be different area included. In fact, the area included would be equal to the net work done by the cycle. So the area included is actually some meaningful parameter. We will see it in the second law of the thermodynamics, which is the last section of this set of lecture notes. And to make up the cyclic processes, there are some intermediate steps. And we would introduce 4 particular cases. The first one is the adiabatic process, in which the Q is equal to 0. So the heat energy transfer is negligible or absent. Remember why you have the Q, why you have the heat energy transfer. It is because you have a temperature difference, or you have a very fast process such that heat energy does not have sufficient time to be transferred from the environment to the system. So there would be 2 possibilities. Either you thermally insulate the system, or you have a process that proceeds very quickly. So heat energy does not have sufficient time for the transfer. That is one special type of a process where Q equals to 0. And the other 3 special processes, they are isobaric process, in which in the PV diagram is easy to understand. Iso means equal. Baric refers to pressure, so constant pressure process. On the PV diagram, it refers to the same pressure between the initial and the final states. Of course, at here, I draw a what we call isobaric expansion, where the volume increases during the process. Equally, you could have isobaric compression. Isobaric compression. where the opposite occurs, the volume decreases. The work done in this case can be quite easily calculated. Remember, once again, it is the area under the process path. Well, or should be the negative of the area under the process path in the PV diagram. So say in the compression case, VI, VF, the work done is minus P VF minus VI. So VF is small, VI is large. The term at the back, negative. This term, negative. P is positive, it's always positive. And so negative P delta V would give you a positive work done in the isobaric compression. Isobaric expansion is having a negative work done because the gas has to expand against a surrounding pressure. This would require work by the gas. Notice the word that I use. There's work by the gas or work by system. I highlight the word by. And there is a work on system. W is the work on system. So a positive W means you are doing work on the system. Negative W means that the work on system is negative, which in fact means the system, well, the external environment is actually gaining energy from the system. So it's actually work done by the system. Notice the playing of the words on and by in this case. So W work done generally is work on system. So a positive value of W means that external environment works on the system. Negative W means that the work on the system is negative, meaning external environment actually gains energy. Where does the energy come from? It must be coming from the system. So that is how we distinguish between the two things. The next one is the isovolumetric process. And in this case, on the PV diagram, there's no volume change. The pressure changes, so maybe from I to F. Notice that if it is the case, initial and final values of the volume are the same. There could not be any work done because the area under this path is equal to 0. So according to the first law, which is at here, delta E must be equal to Q because W is basically 0. There is no change in volume, so the gas does not, but the system does not work on the surrounding, or the surrounding does not work on the system because no volume change. So that is the second case. And the third case of an iso process is an isothermal process, meaning constant temperature process. I will finish this one first before I explain the work done again. So the constant temperature process refers to a process from the initial state to the final state, such that there is no change in temperature. So here you will see a curve, which we usually call them the isotherm, meaning constant temperature line. In fact, if you have this constant temperature line, you could actually relate it to the, at least for the ideal gas law, P times V equals to nRT. If the temperature is constant and the number of gas in the system does not change, it is just the hyperbola curve because PV is equal to constant. And as we will see later, when your temperature is not changing, internal energy of the system does not change. This is the case for the ideal gas. This is the case for the ideal gas. So delta E is equal to 0, meaning that any heat transfer is converted into work done. So that is the case of an isothermal process. And when we consider the work on the system during the isothermal process, we may do the following calculation. But once again, we would give you the equations in the final exam, so there's no worry for doing the integration tour. But here's just to show you how it is done. Remember, if you have an initial state and a final state, the work done in the calculus form is this one, minus P dV, integration from the smallest volume to largest volume. And pressure is related to temperature and volume by the ideal gas law. So we place the pressure by nRT over V. For those who know how to do integration at the end, this would be the result, where you could relate the work done on the system to the volume in the initial and the final states. So that is how we do the calculation. Once again, if you have an expansion, VF should be larger than VI. If you have expansion, VF should be larger than VI. So VI over VF should be smaller than 1. Natural log of VI over VF should be negative. Now, this function, natural log x, if you use your calculator, it is such a button. The meaning of this natural log is to have a log of x with the base number e. This e is what we call a natural number. If you use your calculator to find it, to find the natural number, or you use the Google to find the natural number, it is around 2.7. I remember 2.718, something like that. So that is something you have to be familiar with when doing the calculation of the work done in isothermal process. Isothermal process. Now, I come back to the question by your classmate. The negative of work done by the system. Well, at the first law of thermodynamics, the W, in the first law of thermodynamics, W refers to work done on system. So if you have a positive W, you are having a system, and there is an environment. sorry for the quick writing environment. Now, if W is positive, it means that the environment does work on the system. And usually that means the system would gain energy. Of course, it depends also on the Q. If the Q is negative and it is larger than W in value, then the system still loses energy. But at least when W is larger than 0, the surrounding environment provides some energy to the system. Consider the experiment by James Joe. When he is paddling the water, it would cause the water to heat up. So that is a positive work done. Work done by the surrounding environment, by the external user, if you like, and it is working on the system of water. On the other hand, if the system, say, it is expanding against surrounding atmosphere, it is just like you are inside a house, assuming that you are the gas molecules, you are inside a house, you try to push and expand the room, expand the volume of the room. So you have to do some work. And in that case, you lose energy. So work done on the system in that case is negative because it is not the surrounding environment to work on you. It is the gas in the system to work on the surrounding. So that is the significance of the positive or negative work done. And once again, W by definition, by our definition, it is the work done on system by the environment, work done on the system by the environment. It is the work on system, not work by system. W is work on the system. Work by the system is just the negative of the work on the system, if you like. Okay, now let's take a look at an example. Here you have a 1 mole of an ideal gas, 0 degrees C, expansion from 3 liters to 10 liters. And in the part A, you are asked how much work is done on the gas. So the gas is the system. How much work is done on the gas during the expansion? So you could just fit in the equation. nRT, number of moles, is 1. R is the universal gas constant. Volume change from 3 liter to 10 liter. So in the bracket, VI is 3 liter, VF is the 10 liter. So natural log of 0.3. Please take out your calculator. Just in case you do not know. Just in case you do not know. Let me see if I could find it. You need a scientific calculator. So at here, you have this scientific calculator. Where is the LN? It is the button right next to log. So, sorry. It is the button right next to LOG. So that would be the button you want. I hope you understand which button I'm talking about. So if you press 0.3 and then you press the LN, you would get the value of a natural log of 0.3, which is a negative number because a log of something smaller than 1 should be a negative number. And in this case, you get the work done on the system, which is negative. As you will see, the work done on the system is negative, means that the surrounding actually is receiving energy because the gas is expanding. And then in the part B, how much energy is transferred by the heat between the gas and the surrounding in the process. By the first law, delta E is equal to Q plus W, and it is isothermal process. So internal energy change is equal to 0. All the heat is coming from the work done. So you see the heat energy gain, heat energy provided by the surrounding is 2.3 times 10 to the power 3 joule. Now, see the relation. Here is Q, here is minus W. The whole process is you have Q, which is 2.7 times, well, 2.7 kilojoule actually. And what is the use of this 2.7 kilojoule of energy? It is actually used by the gas to cause the expansion. We would tell later that the internal energy is related to the temperature. And that is actually what I will talk about today. Okay. Some of your classmates is asking as a direct message, which I really encourage you to type the message to everybody so everyone can see. Some of your classmates is asking how we know there is no change in the internal energy. Internal energy is related to temperature in the ideal gas. Internal energy is related to the absolute temperature in the ideal gas. So internal energy change is 0 because no change in temperature. Temperature kept at 0 degrees C. And then in the part C, you return the gas to the original volume and you have the gas to undergo a isobaric process. So now, isobaric process from 3 liter to 10 liter. First, of course, we need to calculate what is the pressure. We have the initial volume, initial temperature, and number of moles. So we are okay to calculate the pressure. Volume change is known. So in this case, you could find out what is the work done. In the isobaric process. Sorry. I should understand it in this way. The gas is returned to the original volume. So it starts in the part C, it starts from 3 liter and well, it starts from 10 liter and ends at 3 liter in the part C. So that is the isobaric process. So P, that is how we do the calculation for the part C. And it's minus P delta V for the isobaric process. Right. We would be having some more of these types of calculations later when we work on, I think, in the heat engines. We will see later. And now we have talked about the first law and we have talked about the work done. I will skip the next two examples because they are not related to the gas, which is not the main concern at here. So I will skip them. At here, I will try to take a very quick look on some of the mechanisms for energy transfer in the thermal process. So when you have a temperature difference, of course, you expect the heat energy to be transferred. How does it take place? How does the heat energy transfer take place? Once again, heat energy transfer takes place because there is a difference in temperature. When there is a difference in temperature, heat transfers take place. But there are various processes that allow this to happen. So you probably have learned them before: conduction, convection, and radiation. We would not go into the mathematics. They are labeled as optional, so I would just very quickly, which is something I believe you have learned before. So it is just a very quick revision on the concepts. Conduction, it occurs due to the collision between the particles in the atomic scale. So you have atoms that when they are at a higher temperature, they would have a stronger movement or larger amount of kinetic energy. And when they collide with the neighboring particles, due to the momentum transfer, you could transmit the energy. So that is the microscopic or atomic explanation of the conduction process. And in general, solids are very good, much better conductors, thermal conductors of heat energy compared with the gas or insulators, because in case of some of the solids like metals, they have, apart from the atoms, they have the mobile electrons, which can help to bring around the kinetic energy. In the case of the solids, you rely on the immobile atoms. And in the case of gases, although atoms are moving very quickly, it is very hard for them to transfer the energy by conduction because neighboring gas molecules are hard to find. They are very separated apart. So collision is very rare. So that is the general case of the conduction. We have the equation for the conduction, but I will not go into the details at here. But in any case, the conduction can take place without any motion of the particles, as testified in the case of solids. Atoms can be staying in their equilibrium position and they could still transmit the heat energy. On the other hand, in the case of liquids or gases, you have another type of effective heat transfer process, and that is the convection. So you are involving large-scale movement of atoms in the liquids and gases. And that is due to mainly the change in the density of the medium. Say in the gas, the hotter gases, they have a lower density compared with cold gases. So if you have a heat source in the room, you would generate a difference of a density for the gas. high density gas, which is cold air, is heavier higher in density compared with the hot gas. So hot gas would rise up, would float up on top of the cold gas, and this would generate some circulation, and that would help for the transfer of the gas particles with different energies, and this would cause the movement of a heat energy, if you like. And finally, we have the radiation, which is yet another type of a heat transfer process. But here, in the case of a radiation, you do not rely on the movement of the particles at all. You just rely on the electromagnetic wave to transfer the energy. And the fact is, all kinds of atoms or molecules, as long as they have a temperature, they would be emitting electromagnetic wave. And that is the reason why when we go through the entrance of PolyU, for example, these days, there would be thermal cameras, because all of us are radiating infrared radiation, although the wavelength is very long compared with the infrared due to, say, some high temperature sources. But we could make use of the infrared from the body to determine the temperature. And the radiation by different objects can be determined by the law called a Stephan's law, which once again, we would not go into the details. And those of you who are interested, you may try to take a look. We will not talk about it at here. So for the heat transfer processes, as we will see, there are three possible types, and we could make use of these concepts to design various products. Say, if we try to provide heat insulation, we would design products that would prevent conduction, convection, and radiation. How do you prevent conduction? You try not to use metals, for example, or you try to use, say, in this jewel flask or thermal flask that keeps the hot drinks at a high temperature for a long time. In a thermal flask, you have various structures that could help to reduce the heat transfer by different processes. You have the vacuum. So the vacuum means that you do not have any air particles between the chamber that contains the hot drink and the surrounding. So in this case, you would reduce the heat transfer by conduction. And also, because you do not have the air particles, you would also minimize the heat transfer by convection as well, because you do not have any flow of the air during the heat transfer process, because the air is simply absent in the vacuum. And finally, the silvery surface inside the thermal flask, according to the Stephan's law, which we have not introduced, they are good reflectors, and that would reduce the amount of a heat transfer by radiation. So I'm sure that you have learned all these concepts before. Originally, they have been included in these lecture notes for more detailed explanation, but from time to time, you find that it takes quite a long time for the explanation, and most of the time, the students would not need it at this level. So we will skip them, and we will leave it to other teachers as other subjects to tell you the various heat transfer processes. For example, ME students should learn it in the year 2, I think. Right, and now we try to move on to the explanation of connection between the temperature and the internal energy. Now, think about it. Temperature is an external observable, meaning that it is basically the property of a whole system. You have a large amount of gas molecules. You have a thermal flask of drinks, if you like, or you have a container of gas molecules. When you measure the temperature, you are just measuring the whole system. Internal energy, on the other hand, it is more related to the energy processed by the particles. So in a certain sense, we are trying to make a connection between some large-scale parameters to the atomic scale phenomena or microscopic phenomena. And that is the very original intention of studying thermodynamics. The scientists at that time, they were trying to make the connection of the external macroscopic world, large-scale observation, and try to relate it to the microscopic behavior, atomic scale behavior. So we have the macroscopic variables related to the whole system, pressure, volume, temperature. They are very useful because we can measure them easily. On the other hand, internal energy of one atom, well, you could hardly measure them. But we are trying to deduce, we are trying to guess what it is like based on these large scale macroscopic variables. So that is the idea. And of course, when we try to do that, we have to make a lot of assumptions because, simply put it, we don't even know how the atoms look like, at least a few hundred years ago. So we are trying to make some assumptions, and the simplest assumption is the case of the ideal gas. But basically, we can always assume, at least for the last 2,000 years, we always assume matter is just a collection of particles, or in the case of gas, it is a collection of molecules. And what we could do is we are trying to make use of the Newton's law. Well, that is the most powerful tool they have 200 years ago, the Newton's law. We try to consider the Newton's law for all the particles. Now we are talking about not hundreds, not thousands, but number of moles of molecules in the order of at least 10 to the power 23, which is a very, very large number. So in that case, we cannot count them one by one. We have to use some statistics in order to guess what is the general behavior. It is not meaningful at all to talk about one gas molecules because there's simply so many of them. Each of them behave slightly different. And we try to have a, if you like, mean value of the behavior. And in particular, the pressure and the temperature, they could be directly related to the motion of gas particles. So let's try to take a look at the assumptions we use for the ideal gas. And based on these assumptions, we would try to deduce the connection between the internal energy and the macroscopic variables. So the assumptions are as follows. First, you have, of course, a large number of molecules in the gas. And they are well separated apart, meaning that you have molecules, of course, each of them has a certain diameter, and the separation between them is much larger compared with the diameter of the gas molecules. So that is a very fundamental assumption. And that seems correct because we know that gas is so compressible, which means that there must be a lot of empty volume in between them. So we could compress them easily. That means large D must be much greater than the diameter of the molecules. And secondly, we assume that the molecules obey the Newton's law. This is particularly true when they are having collisions. But in general, when you have the gas molecules moving independently, according to Newton's law, they would not change their speed unless they are colliding. And they are moving most of the time in a random way, unless they have collisions. Okay. So because you have so many gas molecules, you could find basically equal amount of molecules moving in any direction at any speed at any time, basically. And the molecules, they would have only short range interaction, meaning that most of the time they are not talking to one another unless they are colliding. And fourth point, the molecules would be colliding elastically with the walls of the container. If they are not colliding elastically, after some time, they would all stop. Remember what we mean by the elastic collision? When you hit on the walls, if they lose energy, then eventually they will stop altogether. And that does not seem to happen. So they would be making elastic collisions. And finally, the gas is a pure substance, and all the molecules, they could be assumed to be identical. We don't label them because they are just identical to one another. Now, I'm sorry that once again, we would not go into the details of the deviation. For those of you who are really interested to go into the details, I think in the free textbook, you should have it. So you could refer to the corresponding section of the free textbook. But in general, the idea is you have the molecules, which we simplify it as a single point particle at here, and it is moving with some random velocity at any random direction, vi. Of course, it is in a three-dimensional space, so it could be moving with vi in any direction, but there must be a component vxi, component viy, vyi, and a component vzi. Now, we are trying to generalize the situation. So some of the particles may be moving perfectly along x-axis, that's fine. But in general, the diagram shows the situation. You have components along different axes. And when they are hitting on the walls, there would be bouncing back. So before the collision and after the collision, along the, for example, here, this is the x-axis, and this is the y-axis, and the particle is hitting on the wall, which is perpendicular to the x-axis. After the bouncing, it would keep the momentum along the y-axis because there is no wall or no force provided on the particle along the y-axis in this case. On the other hand, the wall would be providing a action force to push the particle back in the negative XVI direction. See, originally, particle moves along the x-axis with Vxi. After bouncing, it would move with minus Vxi. The reason why they are the same is because the wall is much, much heavier compared with the particle. So the bouncing would be with completely the same magnitude, but opposite direction. So the wall would be providing the action force to push the particle. At the same time, the particle would be providing a reaction force to act on the wall. So the wall would suffer some force. And this is the origin of the pressure, where you have a collection of the particles acting on the wall, and they would be giving you the pressure. So the analysis of the particles all together would tell you the relation between the gas pressure, the mass of the molecules, and the average of the velocity squared. Now, here is a very tricky part, which I do not want to go into details, but as you will see, we are not talking about this quantity, but we are talking about this quantity. What's the difference between the two? The first one is the mean velocity squared. The second one is the mean of the square of the velocity. So now you see why I don't want to go into the details at here, because it is actually quite hard to distinguish the two things. The reason why we stress the use of mean of velocity square is because we are actually considering the energy. So it is actually proportional to the square of the velocity. And therefore, we would have here the mean of the square of velocity in the equation. Taking this aside, we could see that the pressure is related to the total number of gas molecules inversely proportional to the volume. And it is also proportional to this value. Now, what is this value? M refers to the mass of each individual gas molecule. We assume at the beginning that all the molecules are identical, meaning that all the molecules have the same mass. And then we have a collection of these molecules. Each of them may have a different velocity, or each of them would have a different kinetic energy. So here, if you like, this term at here is the average kinetic energy of the molecules. And it is the translational kinetic energy of the molecules. Remember, 1/2 mv squared. So the pressure, as you will see in this equation, it is proportional to N over V. Sorry, it's proportional to N over V. Sorry, number of molecules per unit volume. And it is also proportional to the average translational kinetic energy of the molecules. So with that equation, we could understand how we could change the pressure. You can have more molecules, smaller volume, or you could change the kinetic energy of the molecules. But how do we change the kinetic energy of the molecules? That goes back to the ideal gas law. Because in the ideal gas law, we have PV equals to nRT. PV equals to nRT. Remember what we mentioned at the very beginning. R is actually equal to the Avogadro's number multiplied by a term called the Boltzmann constant. So at here, we are using this trick. We have this, the number of moles of molecules, and then we multiply by the Avogadro's number, and Na times Kb times T. N times Na is actually the total number of gas molecules. So you have the N, which corresponds to the total number of gas molecules. Kb is the Boltzmann constant. T is the temperature, the absolute temperature. So PV is equal to NB times K times T. Now, what is PV? According to the previous slide, PV is equal to this quantity, 2/3 times N times 1/2 m not V squared. We should be missing the not at here. And that is equal to NB times K times T. So simplifying the terms, you would have here the average kinetic energy of the molecule, average translational kinetic energy of the molecules. That is proportional to the absolute temperature, basically. And for gas molecules, this would basically be the energy possessed by the molecules themselves. Remember, in the ideal gas, you do not have particles interacting with one another. So the only energy they possess should be the translational kinetic energy. And that is why we mentioned that the internal energy is proportional to the temperature, because there is no other forms of the internal energy for the ideal gas apart from the kinetic energy. Now, we will see at here we will see at this equation that 1/2 mv squared, which is the total kinetic energy, is equal to 3/2 times kBT. What is this mean? The left-hand side, 1/2 m0 v squared. It means the, of course, total kinetic energy of the molecules. But remember, it is an average value. Now, you would have the energy that could be divided into 3 components. If you are talking about a kinetic energy, just like you have the particles moving in the 3-dimensional space, it is possible for you to consider the motion in 3 directions. So you have a vi, you would have the v along the x-axis, I. Maybe I used the diagram previously. Here, you would have the motion of the particles that could be having a component in the x-axis. Of course, that would also have a component in the y-axis, vyi, and there would be another component along the z-axis. On average, if you take all the particles in the system and then consider the amount of energy in all the 3 directions, it is very reasonable for us to assume, that the energy in any direction should be equal. The average energy in any direction should be equal. I hope that is a reasonable assumption for you, because you have a 2 large number of molecules, and the average energy along any direction in a 3-dimensional space should be equal. Now, that is interesting, because if you assume them to be equal, that means they should be each equal to this value. When you add all the energies together in the x, y, and z axis, that would give you back the total energy given by the equation in the bracket. Now, you will have to tell me which assumption you are talking about. Once again, please type the question for all the students to know. So which assumption we are talking about? Okay, now you have the particles. On the diagram here, you have a velocity which is randomly decided. So there must be some component in the x direction, some component in the x direction, some component in the y direction, some component in the z direction. Meaning that you have certain amount of energy in the x direction, certain amount of energy in the y direction, and certain amount of energy in the z direction. You have so many of these molecules. So the average amount of energy in any of the direction, talking about all the gases, the average amount of energy in any of these x, y, and z directions, they should be equal. Just a reasonable guess, because we do not expect an energy that is larger at one side compared with the other. Otherwise, you would have pressure on one direction larger than the other direction, which does not seem reasonable. So that is why we make this statement at here. And this is a very important assumption that along any direction, along any particular direction, the energy, or along any of the axis, the average energy is equal to 1/2 times KB times T. This is something we call the theorem of the equal partition of the energy. And this theorem plays a very important role in determining more complicated systems. And here, we would be considering only atoms that have assuming only molecules that have only one single atom. And so their energy is only in the translational sense. They only make translational motion. But in fact, when you have molecules that are made up of more atoms, then the molecules themselves, they have other what we call degrees of freedom. Apart from just moving in the X, Y, Z direction, they could actually be rotating about their center of gravity. So there would be some further degree of freedom. By the theorem of equal partition energy, whenever you have more degrees of freedom, you just add in 1/2 kBT in the calculation. So that is the idea of the theorem of equal partition of energy. Each degree of freedom would contribute 1/2 kBT to the energy of the system. And it really depends on how many degrees of freedom you have for the molecules to have the motion. At least for the one atom molecules, the total kinetic energy is equal to 3/2 times nRT. Now, degree of freedom of motion refers to what direction or what sense they could have movement. Say, if you have point particles, the major energy comes from their motion in the three-dimensional sense. So it could be x-axis, y-axis, or z-axis. Of course, at any time, you could have some particles moving only parallel to one direction. But on average, you have a lot of particles, so you must have equal amount of particles moving in x direction and equal amount of particles in the y, equal amount of particles in the z direction. The energy should be equal in the three directions for all the collection of particles. When you have particles that do not have single atoms, as we will see a little bit later, well, we could go to that for this point, maybe, if that would satisfy your curiosity. Here, you have particles or molecules that are performing translational motion. So this is a two atom molecule. So the center of mass is moving along the x-axis. And of course, some of them will be moving along the y-axis, some of them moving along the z-axis as well. So there would be 3 degrees of freedom, x, y, and z. On the other hand, molecules can be rotating about their axis. Rotation about the y-axis in this case, that means rotation about the line connecting the two atoms does not really contribute a lot of energy, because according to what we learned in the moment of inertia, the atoms have the center of mass that is along the axis of rotation. and the moment of inertia would be close to 0. On the other hand, rotation about the x-axis and the z-axis is like rotating the dumbbell for the two heavy masses on the dumbbell. So that would contribute to the degree of freedom of motion, and there would be two of them. So by if you have two atoms in the molecule, you actually would have the additional contribution to the energy by the rotation, by the rotational motion. And actually, if you are having an even higher temperature, vibrational motion would contribute to the energy as well, but we would not try to drag on at this point. So the main idea at here is that when you have particles that are performing translational motion, the total kinetic energy is related to the temperature. And therefore, for the gas molecules, which are simple systems of particles with no interaction at all among themselves, the total kinetic energy is equal to the total internal energy. So for simple molecules, the internal energy is just equal to the total kinetic energy or total translational kinetic energy. So it would be proportional to the temperature. That is the main idea for this deviation here. So if we have a gas with only translational energy, then this is the internal energy of the system. So this part. And this tells us internal energy depends only on temperature. So that is the main idea of this deviation. Internal energy of the simple ideal gas depends only on temperature. Now, let us consider the case of a helium, which is very close to an ideal gas, because, and in particular, the molecule of the helium has only one atom. So that is even more close to what we have just discussed. So you have a helium of a certain volume, 3 meter cube, and there is 2 moles of a helium gas at 20 degrees C. And we now assume that it behaves as an ideal gas. So what is the total translational kinetic energy? For the helium, the total internal energy, the translational kinetic energy, as we just discussed, is equal to 3/2 times nRT. The translational kinetic energy is equal to 3/2 nRT, referring to the translational motion of the molecules. No rotation, no vibration, just the translation. So that is given by 3/2 nRT. N is the number of moles, R is the universal gas constant, and T is the temperature. And 20 degrees C, so that is the total translational kinetic energy. And the average kinetic energy per molecule here, the average kinetic energy per molecule it is equal to 3/2 times kBT. And that is kB is 1.38 times 10 to the power minus 23. Temperature is 293 Kelvin. So for one molecule, the average kinetic energy is this number for the helium gas at 20 degrees C. Of course, this is an average value. Because you have so many of the gas molecules, we could do statistics to calculate the average value. In any particular direction, the kinetic energy would be equal to 1/2 kBT. And the total average kinetic energy is 3/2 kBT. Now, why do we need to talk about all these energies? It's because when we are trying to put the heat, or when we're trying to change the temperature of the molecules, or when we are trying to change the temperature of the system, actually, it involves sometimes a change of the internal energy. And that would be related to the amount of heat supplied to the system. So at here, we try to understand what is the specific heat for heating up 1 mole of gas molecules. And that is something we call the molar specific heat. And there are different processes in which we could heat up the gas. Of course, when you are heating up the gas, you could take different paths. So here, you may have initial state at I. Initial state is at I. And you may decide to change the temperature of the gas from T to T plus delta T. From T to T plus delta T. So there are different possibilities for you to change the temperature. So here in the PV diagram, there are different paths. One is to the final state F, the other F dash. The third one is an F double dash. Remember what we have just mentioned. Internal energy of the system depends only on the temperature. So it means the internal energy of all the final states should be equal in this case, meaning that delta E is equal for all the 3 processes. The change of temperature is delta T. And if the internal energy change is only related to the temperature change, delta, well, because if, as we just seen, EINT, the internal energy is proportional to temperature. So delta E should be proportional to delta T, nothing else. But at the same time, when you are heating up the gas from T to delta T, you do not simply provide the change in the internal energy, because from the first law, delta E is equal to Q plus W. Delta E is equal to Q plus W. So the heat supplied, as we would expect for the molar specific heat, the heat supply is not simply for changing delta E. It could be used for changing it could be used for the W as well. So it depends a lot on the path taken. And in particular, we will see two cases of the molar specific heat. And the specific heat for the two processes would be the change in the constant pressure and the change of the temperature in a constant volume case. So what we call isobaric and isovolumetric processes. In those two cases, when you change the state from I to F, there is a change in temperature. So this would involve, of course, a change of internal energy, but at the same time, you have to supply the heat to do the process. So we try to determine what is the value of Q in the two processes. So for the two processes, we would define the amount of heat energy required to bring about the temperature change. It's equal to NC delta T. Remember the specific heat we talked about in the previous lecture slides. Q is equal to MC delta T. If you go to, I can't remember which page, this equation for the specific heat has appeared, and the equation is valid for the liquid and solids. And it does not depend on the process, because in the case of a liquid and solid, the volume of the liquid and solid does not change a lot when you heat up the liquid or solid. So different processes does not apply in the case of a heating or cooling of liquid and solid. But in the gas, the process determines a lot because the work done is involved. So for the two types of processes, constant volume process and constant pressure process, we try to define what is the amount of the heat energy required by these two equations. Of course, the two equations look exactly the same in format. The main difference comes from the quantity Cp and Cv. Now, how would you expect the two processes to occur? In the PV diagram, P versus V, when you are talking about change of temperature, so you have this isotherm corresponding to T, and you might have some initial state I, another isotherm corresponding, another isotherm corresponding to delta T plus T. So a change of temperature. And there are two possibilities. One is, T plus delta T. So there are two possibilities. One is constant volume process. So let us say it's a constant volume process, FV. The other one is the constant pressure process. Notice that they have the same final temperature, meaning that the internal energy change is the same. And there is no work done in the case of the constant volume process. Work done is 0, which means that all the heat energy supplied in the constant volume process would be equal to the internal energy change. Now, this would be very useful because in any different types of processes, no matter you are doing constant volume process, constant pressure process, or any other funny processes like the ones shown at this diagram, as long as you have a change of temperature delta T, the amount of internal energy change can be calculated by the equation shown at here, NCV delta T, regardless of the process. Because in the constant volume process, all the heat is used for internal energy change. So we could make use of this fact to calculate the internal energy change by the NCV delta T equation. On the other hand, in a constant pressure process, apart from internal energy change, you have the work done. So you could say in the constant pressure process, the heat involved is equal to NCP delta T, which is of course what I have on the lecture slides, but it should be equal to internal energy change plus the work done, which is the first law of thermodynamics. What is the internal energy change? As I just written down at here, the internal energy change can be represented by NCV delta T. What about the work done? It is equal to minus PdV. No, I should rewrite it a little bit. Q is equal to delta E minus W. Q is equal to delta E minus W according to the first law. So W is equal to minus PdV. So it minus W is equal to PdV. So it's P delta V. And if you are having the ideal gas law, PV is equal to nRT, when the process is a constant pressure process, when the pressure is constant, N is constant, R is constant, P delta V should be equal to nR delta T. So that is why this is equal to NCV delta T plus nR delta T. You could see the connection now between CP and CV. So for the any of the gas, the CP and CV, they are related to one another by a difference of R. So that is something we will see in the coming slides. And here, we will be mainly looking at the case of the monoatomic gas. So molecules with only one atom is referred to the monoatomic gas. This would refer to the case of the inert gas, for example, helium or argon, and so on. And when you add the energy to this type of a monoatomic gas, any of the energy change is used for changing the translational kinetic energy. So in this case, the internal energy for the monoatomic gas, internal energy is equal to 3/2 times nRT. And the internal energy is proportional to temperature. Therefore, internal energy change is proportional to the temperature change. And the internal energy is, in general, a function of temperature in the ideal gas. For any of the gas, any of the ideal gas, the internal energy change is equal to NCV delta T, because all the heat energy is used for changing the internal energy. No work is done in the constant volume process. So this would be a useful equation to decide what is the internal energy change when you have a change of temperature. Although the equation, strictly speaking, is for calculating Q, but it could be equally valid for calculating internal energy change, as long as you know the temperature change. And for monoatomic gas, CV, as we'll see, is equal to 3/2 times R, because as we have just seen at here, E is equal to 3/2 nRT. Delta E would be equal to 3/2 times nR delta T. But remember, delta E is equal to NCV delta T. NCV delta T. So comparing the two, you will see CV is equal to 3/2 times R. So that is the idea of the finding a CV molar specific heat for the constant volume process in the monoatomic gases. And the difference between the CP and the CV, as we just explained, is equal to R. So we could get the CP quite easily as well. CP is just R plus CV. So it is 3/2 R plus R, that is 5R divided by 2. For the constant pressure process, the molar specific heat is 5R divided by 2. Right. And later, we will see a very important parameter called the ratio of molar specific heats. And that is the comparison of the specific heats in a constant pressure process and a constant volume process. For the monoatomic gas, monoatomic ideal gas, the ratio of the molar specific heat is equal to 5R/2 divided by 3R/2, and that is equal to 1.67. Well, how do we get the, okay, some of the classmates have been answering for me, hope, which you can go back to the lecture notes at here for my deviation just then. The comparison. Yeah, you could just take a quick picture of this slide using your camera and try to understand what it is. The main reason is because you have the definition of Q equals to NCP delta T in a constant pressure process. But the Q is equal to, according to the first law, internal energy change minus W. W in the constant pressure process is P delta V, which is equal to NR delta T. So that is why we get the equation. So for the monoatomic gas, that is the values of a Cp and Cv. For other gases, this might not be true. As you will see, for monoatomic gas, Cp, if you turn it into values, 20.8, Cv around 12.5, so quite constant. But for diatomic gas, where you have two atoms in the same molecule, Cp and Cv changes. But you will see the similarity between Cp in the monoatomic gas and the Cv in the diatomic gas. That is somehow related to the eco-partition theory, which I should not go in the details at here until maybe a little bit later. So I think at here, maybe we just take a look at an example before we go any further into the discussion. Now right here, you have a gas cylinder containing 3 moles of a helium gas, so monoatomic ideal gas at 300 K. The gas in the part A is heated at constant volume. So in order to heat it up, you need to transfer heat energy. How much energy must be transferred by heat to the gas in order to raise the temperature to 500 K? It is a constant volume process. So you have NCV delta T. CV for constant volume process, the molar specific heat for constant volume process. And for monoatomic gas, CV is 3R/2. R is the universal gas constant. If you look it up, it should be 8.314 if I remember. So it is 12.5 at here. Unit is joule per mole per Kelvin. Delta T is a change of temperature, 500 K minus 300 K. And in this way, you calculate the heat required to heat the gas up to 500 K at constant volume process. Now, in the part B, you try to calculate the amount of heat required for heating the gas up at constant pressure process. So equation changes. In the part A, it is CV. Here, part B, CP, constant pressure process. And for the monoatomic gas, CP is equal to CV plus R. That is equal to 3R over 2 plus R, and that is 5R divided by 2. So you see it's 20.8. All the others are the same. So it's 12.5 kilojoule of energy. So it's just a quick demonstration of how we should handle different processes of heating. When you have different processes of heating, you may involve different amount of heat energy. Although the internal energy change would be the same if the temperature change is identical. Delta E is the same if delta T is identical. That is the main message at here. Now, of course, if you are trying to heat up the gas, you expect a change in temperature. So that is why we are not discussing about constant temperature process. When you have a constant temperature process, delta T is 0. So internal energy change is 0. That is the idea. But what about a diabatic process? Well, in the adiabatic process, according to definition, Q is equal to 0. So any internal energy change must be coming from the work done. In that case, we have to be more careful in our calculations. And let us try to analyze, at least in terms of discussion, analyze what is the situation. When the Q is equal to 0, basically there is no energy transfer as heat. And all the parameters, they could change. Remember, in the free iso processes, constant volume, constant pressure, and constant temperature. Sorry, constant temperature is not this one. Constant temperature. At least you have anything of P, V, or T that is constant. But in the adiabatic process, all of the things could change. But at least we are sure about two things. First, Q is equal to 0, no heat supplied for the change of state, for the change of initial state to final state. And secondly, it is ideal gas, so ideal gas law is still valid. In fact, with some deviation, we would obtain a very important relation between pressure and volume in the adiabatic process. And that is P V to the power gamma. It is equal to constant in an adiabatic process. So if you go to the next page, you will see the situation. Here, the initial state is I, final state is F. And the adiabatic process happens as a expansion. So the final volume is larger than the initial volume. When you have such an expansion, according to the first law, delta E is equal to W because Q is 0. When the work done is negative, which happens in the expansion case, work done is negative. When the work done is negative, delta E is negative, meaning that the temperature of the gas should drop. So that is why final temperature is smaller than the initial temperature. So for the adiabatic process, Pi times Vi to the power gamma is equal to Pf times Vf to the power gamma. Or if you substitute the P on the two sides by the ideal gas law, you would have the second relation as well. Ti Vi to the power gamma minus 1 is equal to Tf Vf to the power gamma minus 1. Sounds fairly complicated. So once again, it's better to take a look at an example. So at here, you have the adiabatic process for changing a gas from an initial pressure of let me see, at a temperature 20 degrees C from an initial pressure of 1 atmosphere and volume 800 cm cube to a volume of 60 cm cube. Now, because the process is adiabatic, and it is an adiabatic compression, and we are asked to find out what is the final pressure and temperature. We could make use of the adiabatic relation Pi Vi gamma equals to Pf Vf gamma, adiabatic relation. And it is given to you, gamma is equal to 1.4 for the gas. So you just substitute the numbers basically into the equation. Initial pressure 1 atmosphere, initial volume 800 cm cube, final volume 60 cm cube. So this would give you final pressure 37.6 atmospheric pressure. And final temperature can be calculated either by the other adiabatic relation at the bottom of this page, or you could simply use the ideal gas law. Pi Vi over Ti equals to Pf Vf over Tf. And remember just that temperature has to be in the unit of Kelvin. It's an absolute temperature scale. So that is how we handle the problem. We have mentioned just then the equal partition of the energy. So far we have been focusing on the monoatomic gas, where you have the translational kinetic energy to contribute to the internal energy. When you have diatomic molecules, rotation of the molecules would also contribute to the internal energy. P1V1 is not equal to P2V2 because we are not having constant temperature process. It is the adiabatic process. And why gamma is involved, we need to derive it, but that is not involved here because we need to use calculus. If you're interested, you may have to refer to the textbook for the deviation. So we are just using the relation at here for the adiabatic process. Now, if we are considering the diatomic molecules, then we will start to involve the rotational kinetic energy. According to the theorem of the equal partition of energy, at the lower temperatures, we would involve the rotational motion, and there are 2 degrees of freedom for the rotational motion. As we just explained, in the rotational case, here, rotation about X and Z axis would contribute to the rotational kinetic energy because I is significant. Rotation about the Y axis is not significant because the low or small value of the moment of inertia. So 2 degrees of freedom for the rotational motion. Therefore, for the internal energy in the diatomic molecules, CV is equal to 5/2R because internal energy is 5/2 nRT. Equal partition energy, 5 degrees of freedom, meaning that 5 times 1/2 kBT for the internal energy contribution to each of the molecule. So the total internal energy is 5/2 times nRT. CV would be 5/2R. CP is CV plus R, so it's 7/2R. That is for the diatomic molecules. And we better stick just to the diatomic molecules for the explanation, for the discussion at here. And I think we would probably stop at here. We will not be going into extremely high temperatures because in the extremely high temperatures, you also involve vibration, but we are not touching upon this point, at least in our discussion at here. So what we are left behind is the last topic of the heat engine and the second law of the thermodynamics, which we will deal with in next week. But please attend the lesson next Monday because I would need to make some important announcement concerning the examination. You may be receiving an email very soon that the final examination should be conducted completely online, not only for students overseas, but also for students in Hong Kong. So we would have some explanation on how this is to be done. And we would have to make use of the Monday lesson to do some explanation. So please make every effort to attend the lesson on Monday. And I would stop the lesson at here. We should finish the last topic of the lecture notes in next week, okay? Well, once you click in the website for the first volume, try to play around with the website and you should find the volume 2.